So this is color theory and optical obstacles simulating myopia with a camera. So you may be familiar with the look of these exercises. These were introduced by Joseph Albers when he was a professor at Yale University. He had his students do many exercises with color theory. And after reading through his book called The Interaction of Color, I became fascinated by these two exercises in particular. So I ended up wanting to recreate my own in Photoshop with my own colors. So the trick is seeing whether these two inner squares are the same or different. And these two animations show that the two inner squares on the left are the same, and the two on the right are actually different in saturation. And the way that Albers was able to create this effect was by having these two inner squares share the same color in saturation, and then by having these two ground colors be equidistant from the shared color in the middle. And that made this less saturated color, and then this same saturated color, it appears darker on this one because it's sitting on a lighter ground color, and it appears lighter on this one because it's sitting on a darker ground color. And for making two colors look like one, he picked two that were less saturated and then two that were more saturated, with the less saturated sitting on the more saturated and the more saturated sitting on the less saturated, and that made these two seem more similar. And so what happens to the effects of Auer's color theory and its illusions for people who are myopic or nearsighted? So that means that we are not receiving the same amount of information about the light that people who have 20/20 or perfect vision can see. So that is depicted with this chart of these light rays. So these light rays are entering the eye, and then they focus at a point that is well before the retina, and that means that the retina is receiving blurred images and blurred information about the light because these are not focusing at a point that is on the retina. Wherefore, the concave lens actually fixes this by slightly fracting these rays, and then they can focus on a point that is on the retina. And so what is meant by 20/20 vision? So Snellen was an ophthalmologist who actually introduced this chart, which many of you are familiar with, which is used to measure visual acuity. So Snellen said that by standing 6 meters apart, we can measure visual acuity by seeing how many lines we can read. So I figured the best way to simulate this for people who have 20/20 vision or not the same vision that I'm presenting on this PowerPoint is by using a camera, and that is because of the many ways that the camera parallels the human eye. And so what we do is we put a concave lens in front of a camera, and then we hold down on the image we want to focus on in the background with the lens in front of it, and then we get this yellow button that says autofocus lock. When we take away the lens, we're actually going to see a blurred image, and that is because we just tricked the camera into thinking that the light rays are converging before the camera film, similarly to that diagram on the last slide where the light rays were converging before the retina. And so these are the results of the simulated vision. So from 6 meters away, the 20/20 vision looks very similar. And then for 6 meters away for the myopia, we're actually losing a lot of information about this color and a lot of information about this color. And this square is increasingly smaller. And so is this one. It's sort of blending in with that white background because it is already desaturated to begin with. So why is this? Well, it's obviously easier to tell that these two inner colors are the same when they are closer together or side by side, but even when they're slightly separated, let's call this the x distance. As the x distance increases, we are seeing that this is much harder to tell that these two colors are actually the same. This one is appearing darker because it's now sitting on its lighter ground color, and vice versa for this one. So what happens is we increase the z distance, and let's say the z-axis points outwards towards the viewer. So the viewer is seeing this image from further away, 6 meters, and now we're receiving less information about the light, again, because the light rays are converging at a point that is well before the retina, which means that we're not getting the best information about the light. And because color needs light, and because color cannot exist if there is no light present, or color cannot be seen if there is no light present, that means that we're having this gap. And this gap is increasing because we are losing the acuity and we're losing this edge into this white edge. Everything is blending together. So this distance is slightly increasing, which means that this distance is perceptually increasing by a little bit. And now these colors, this one seems much darker and this one seems much lighter. So the effects of his color theory are actually heightened for a person with myopia.